I'm going to present the work that we have been doing under the project related with estimating solid-solid interface energy of the aluminum-rich aluminum zinc alloy, and I'm going to describe the methodology we have followed and also the reasoning as to why we have followed this kind of methodology. So this is the work done by two of my students, Ankush Deshmukh and Abhishek Kumar. And this is in collaboration with Gurrajan from IIT Mumbai and Abhik Chaudhary from ISC Bangalore. And of course, we are very grateful to NSM and DST Sub for the funding for both these students and the computing support that the NSM facilities at ISC and IIT Kharagpur had provided for doing these calculations. And a large amount of the work we have also carried out in-house under an HPC cluster that was funded under the DST Nano Mission project, which is called Sahasrara. So my talk is going to be a little different than what you have been hearing so far, because this is not in the micro scale regime, but this is in the atomic to nanoscale regime. And we are going to use this regime to get or obtain the solid-solid interface energies. So when we think of an interface, what is it that we have in mind? So we have in mind surfaces that are going to differ either in phase structures and orientations. They could be differing in phase structures, orientation, and or compositions. And as an example, I have put in an experimental work there that shows how the evolution of interfaces happens over time, how you see the aging has affected the structure of the different regions in the interface. So the primary reason this happens is because of the lattice mismatch that is there between the different phases of the crystal structures, or because of the different compositions of the crystal structures that are there. So because of this lattice mismatch, there is a difference in the what we call as the interfacial bonding, and which is the primary reason for everything that happens related with the evolution of this interface structure over a period of time, and as well as how it will affect the mechanical behavior. So if we want to understand the later part, the evolution of the microstructure, if we understand what is the strength of the interfacial bonding and how that is going to affect the evolution, then it gives a handle to be able to predict the properties. So to be able to measure this interfacial bonding strength, we need to determine what is called as the interface energy. So how do we go about determining the interface energy? So when we looked at literature to try to figure out how to determine the solid-solid interface energies, we really had a difficulty in trying to find a very clear, let me say, methodology or a clear path that explains how one would be able to obtain the solid-solid interface energy for any kind of surfaces that one is interested in, or interfaces that one is interested in. So there are some reports in the literature from first principles calculations where they have described that the methodology is very simple, as you can see here. Okay, all you have to do is, if you know what is the orientation of the two surfaces for which you want to determine the interface energy, then all you need to do is form an interface of them. and you obtain the energy of the individual surface. So if I were to take just one part of that interface separately and do the calculation for that, and I now do the same calculation for the second part. Okay, so that will give me the energy for individual surfaces. And then I put these two surfaces together and now again do the same calculation and obtain the energy for the combined structure now. And the difference in energy between the combined structure with respect to that of the individual surface structures should give me the interface energy. So it looked like there was a nice simple way to do this. However, when we started to do this in practice, we realized there are difficulties in doing this. So let me just take you through how we have gone through this process. So to be able to construct the surface, first we need to know for any material that we are interested in, what is the crystal structure for that material, and for that crystal structure, what are the structural parameters, and this we can obtain from first principles calculations. So if we know the crystal structure for aluminum, we know that is FCC. For zinc, we know it is HCP. So we take this structure, we do a calculation, obtain the bulk structural parameters. Then from this, now we can do a repetition of this bulk unit cell and generate a large structure. And from this structure now, we can cut off surfaces of desired orientations. And then once we have this surface of desired orientation, we should be able to obtain the surface energy. And similarly, these desired orientation surfaces we can put together and be able to get the interface energy. So what I have shown you here is the structure of aluminum, zinc, and two of the aluminum-rich zinc alloys that are of interest to our materials engineering team here, which was we have chosen the 95.5 AL95 zinc 5% doping and zinc 10% doping in this. So how does one obtain the bulk structure parameter? So for this there is a set methodology. I'm not going to go into a lot of detail, but just give you a flavor of how this is done. Is there some problem?
There was something coming up.
Yeah.
That's right.
So how do we obtain the bulk structure parameters? Okay, we perform what are called as total energy calculations, and using this we perform a lattice optimization. Lattice optimization is very simple. All you do is you contract the lattice and you expand the lattice, and for each of these contraction and expansion you have done, you calculate what is the energy, and then you plot the energy for each of these lattice variations you have done. Then where the point or the lattice for which you get the minimum energy is basically the structure that the material likes to be in. Okay, and typically this has been from first principles. It is known that the whatever lattice parameters you obtain give a very good agreement with the experimentally obtained structure parameters. Although this is what is considered as a 0 Kelvin theory, meaning there is no temperature in the calculations and the experiments are performed at a certain temperature, the agreement between the prediction from the theory with the experiments is very good. So again, I'm going to give this very briefly. I'm not going to put in any equations, but just in layman's terms, how do you understand how the total energy calculation is performed? So because you're interested in getting the total energy for any structure that you're interested in. So in this case, now the structure is comprised of ions and electrons that are moving around these ions, the total energy has a kinetic energy component and a potential energy component. So we have to have a formulation to get the kinetic energy of the ions and the potential energy from all the interactions that are experienced by the electrons that are moving around the ions and the ionic motions. So there's a formalism of doing this. So we get the kinetic energy of electrons. We calculate the ion-ion interaction energy, the ion-electron interaction energy, the electron-electron interaction energy. And what is not considered here is the kinetic energy of ions. And this is because the calculations are performed under what is called as the Born-Oppenheimer approximation, where it is because the ionic motions are very sluggish. By the time a particular ion moves, the electrons would have actually made all the adjustments that are required under a particular potential. So it's like a tortoise hair, you could say, problem. Okay, by the time the tortoise has moved one step, the hare would have performed a few thousand rounds around it. So effectively, the electron sees that the ion is stationary. So which is why we don't consider the kinetic energy of ion. So we only consider, but we do consider the effect of the ion on the electron. So, and there are a few other approximations which are required to determine the accuracy of the total energy and everything that is related with the physical behavior of the system. So these approximation, one is a very important one, which is called as the pseudo-potential approximation. It is very important because it reduces the complexity of the calculations and yet it gives us very good results. And this approximation helps us to treat the electron-ion interactions. And for the electron-electron interactions, there are certain parameterizations that have to be performed to treat the exchange and correlation part of the electrons. There are different exchange correlation functionals. So sometimes we have to figure out which one is going to work well for our system. So in this case, we have worked with what are called as Pau pseudo-potentials, and we are going to use the PB exchange correlation functionals. And with this, now we perform the structural optimizations for aluminum, zinc, and the aluminum zinc alloy, for which we are interested in obtaining the solid-solid interface energy. So we do the optimizations until the forces on atoms are reasonably well converged, and the total energy of the system again is reasonably well converged. So with this, then when we do the total energy calculations, optimizations with respect to the lattice parameters, then we compare what is our calculated lattice parameter and how it compares with what is reported in experiments. So the figures in blue are the calculated ones, and the experimental one we have put in the brackets. So you can see that this comparison is very good. So for zinc, for aluminum, both of them, the comparison is very good for the A and the C lattice parameter. So now if I want to construct an interface, I have to put two surfaces together, and because we know that these are two materials where the lattice parameters are varying by a they have a significant amount of difference in the lattice parameter. So we figure out what is, or we calculate, let me say, what is the lattice mismatch between the zinc and aluminum. So we see that for the if I were to interface pure zinc with pure aluminum, then in the A direction I have a 51% lattice mismatch, B direction same amount of lattice mismatch, and for the C parameter I have 18% lattice mismatch. Now if I dope it with zinc, then based on what is the amount of dopant we have, this lattice mismatch changes. And because for zinc we know A is much smaller than the A of aluminum, doping we can understand is going to reduce the lattice parameter for the aluminum rich zinc system. So we see that this lattice mismatch decreases. But this decreases, we have to keep in mind in the A and B direction, but it increases in the C parameter. Okay. So now we have the bulk structure. We know what is the lattice mismatch. We can generate a surface for aluminum. We can generate a surface for zinc. We can put them together. We can generate an interface. So the orientation of the interface here, as you can see, is given here. This is the Z direction, and along this, aluminum is oriented in the 1 direction, and zinc is oriented in the 0,0,0,1 bar direction. And the X and Y directions for aluminum and zinc are chosen to be again complementary to one another in such a way that the lattice mismatch will be minimal. So now this is a large unit cell, let me say, that we have to work with to be able to get such a small mismatch along the X and the Y direction. Because if we look at what is the original mismatch, it is 51% in the A and B direction. So by repeating that one single cell structure, okay, many times, we are able to reduce that lattice mismatch and bring it to 0.09%. Now similarly, we did this for the aluminum 95 zinc 5 and the aluminum 90 zinc 10. I'm just going to show you the result for the 95 zinc 5 interface. And in this case, we see that now, because the original lattice mismatch between zinc and aluminum doped with zinc got us a small reduction in the mismatch. So this mismatch now is much less than what we see in the pure aluminum, pure zinc case. Okay. However, to be able to get this kind of a reduction, we need to work with a far larger supercell, where you have to take 175 units along the X direction for the aluminum 95 zinc 5 and 58 cells along the B direction. And similarly for zinc, we have to go 188 repetitions in the X direction and 54 repetitions in the Y direction. So now we have a surface that we can generate. We have an interface that we can generate. We know what are the dimensions of these surfaces we need to work with. So, and what is the area of the surface we would be working with. So this comes in some nanometers. And what is the number of layers or what is the number of atoms per layer we would have to work with. So in this case, it comes out close to 9,000. For the aluminum zinc interface, it comes out close to 9,000. Whereas if we look at the aluminum 95 zinc 5, it comes out very close to 100,000 atoms. And this is only for one single layer that we are considering in a particular orientation of that surface. Okay. And for 9010, it comes out to be close to 20,000. So this was a problem now. We cannot really solve by first principles method, because this amount of atoms cannot be even in the best, with the best computing infrastructure we have anywhere in the world. We cannot do this by first principles. So we, because we are interested in the solid-solid interface energy for the aluminum zinc system, okay, we know how to get the interface energy. There is a methodology, okay, sorry, that tells us that construct the interface, obtain the energy of the interface. Once you have the energy of the interface and the energies of the individual surfaces, you simply apply this mathematical equation and you should be able to get the number you are interested in. So the surface energies for the individual surfaces we can still obtain by ab initio methods. but the interface energy we cannot obtain. So, which means that we have a methodology which we really cannot use because it's just not practical. So then we thought, okay, let's go and find an alternate approach where we do not work with first principle simulations, but we perform classical molecular simulations where we are able to handle a very, very large number of atoms, and so this number of atoms should not be a problem to handle by classical molecular simulations. However, if we want to use this approach, we need to first validate whatever is the calculation that we are performing by classical approaches is giving us the right answer. And now if we have to validate, we have to again resort back to first principles method because they are more accurate and they have a better agreement with the experimental results typically. So we must be able to compare the results from the classical simulations with ab initio simulations, one. Second, when we want to look at the solid-solid interface energies, when we want to do a simulation, we need to be able to determine how large should be the surface thickness that we need to consider when we perform the interface energy calculations. And one way to be able to determine what should be the thickness of the interface is to find out typically experimentally what are the surface thicknesses that are observed in experiments. However, in this case, there is no experimental data that is available. Now, since there is no experimental data available, we need to have an approach that would give us a reasonably correct slab thicknesses to use with. And this we can do if we can find out for what thickness the surface energy of these slabs converges, which means that I start doing a calculation for different numbers of slab thicknesses. I look at the energies of these each of these surfaces, and I should be able to see that the surface energy has reasonably converged. So we need a system where we will be able to work with these three things. We should be able to compare our results from ab initio with the classical simulation, and we should be able to compare the surface and the interface energies. Okay. So this meant, of course, the surface that we are interested in, we know we cannot handle by ab initio methods, which means we cannot use the aluminum zinc system to do this validification of the energetics. Okay, so we chose the interface where we would be able to do this. So fortunately, we were at this time we were also working with the interface for the titanium BCC and the titanium HCP system. And it so turned out that for the particular orientations that we had chosen for the titanium HCP and BCC solid-solid interface, we were able to actually work with a very small, what is shown here, simulation cell using ab initio method. So if I were to repeat what you see here, if I repeat this structure along the x direction and the y direction, I am able to get back this structure. Okay, so this is periodically what we say, it has a periodicity in the x and the y direction. So then this, so what you're saying here is 24 layers of the titanium BCC interfaced with 20 layers of the titanium HCP. And in this case, the lattice mismatch along the x direction is 1.1%, along the y direction is 3.9%. Although lattice mismatch is large, what we saw is that whatever the number of repetitions we do in the x and the y direction, this lattice mismatch stays the same. So which is one of the reasons why we are able to work with this small system in this case. So now we have a system where ab initio simulations are feasible, and then we can use this to also find out what the energy profile would look like in the classical simulation. So we know how the interface is. So how do we determine the surface energy? I told you how to determine the interface energy. To be able to determine the interface energy, I also need a component of surface energy. If we go back quickly to that slide, this equation, right? Here is the surface energy component. Okay, so and this is the energy obtained for the interface. Okay, so how do we obtain this surface energy? So this surface energy we obtain by working with a simulation surface, which we know we can extend in the periodic x and y direction, and we get the energy of this surface, and from that, so we apply simply this mathematical formula. We subtract the energy of the bulk and multiply that with the number of atoms that are there in the simulation of the surface. Okay, and we have to have that factor of 1/2 to account for the area of the surface. And when we do the surface calculation, we have to ensure that there is a vacuum in our simulation between the topmost layer of the surface, so that because these are periodic repetitions along the x, y, and z direction, there is no interaction between the top layer in the simulation cell and its periodically repeated images. So there has to be enough vacuum between the topmost layer of the surface and where your simulation cell ends. Okay. So now, so this is what, so we have a methodology, as I said. So now we simply do the surface energy calculation using first principles and the classical simulations. So for the classical simulations, we use the software lamps, and we use the for titanium, we have used the titanium mean potential that is developed by Henning et al. It's taken from the NIST library for EM potentials. So to do the surface simulations, we fixed the bottom 2 layers, and for the HCP surfaces, we fixed the bottom 1 layer, and for all other layers, we are allowing them to relax completely in the Z direction. We are not allowing them to relax in the X and Y direction because we want them to hold, we are mimicking the bulk. So in the X and Y, they are not allowed to relax. So if we look at now how, so this n tells you what are the number of layers that we have used in this simulation, and this is the energy that we obtain for each layer. So each number there, let me say if I have 4 layers, then that is the energy. If I have 24 layers, then that is the surface energy. And the same simulation we repeat through the classical molecular simulations, and we look at the energies. Okay, so for the HCP, we see that the energy is very nicely converged by, actually it's converged by 12 layers, we can see, but unless we do a few more layers, we won't know whether it is converged or not. And for the BCC case, we see again they are fairly nicely converged till the 3 decimal places. You see that they are in agreement. Okay. But if we look at the energies that we get through the classical simulations, then one, the numbers don't agree. The surface energies that we are getting from the ab initio simulations are not the same as the surface energy that we are getting from the classical simulation. So that's the first problem we have, that the surface energies are not matching. And the second problem we have is that the convergence behavior that we see from classical simulation is very different than the convergence behavior that we see in the ab initio simulation. So what I mean by the convergence behavior? So if you look at, for example, this case, okay, so here we see that the energy begins at some number and then it slightly increases and then it stabilizes around a particular number. Similarly, for BCC, if we look at here, again, the energy starts at some number, okay, and then it increases and it has more or less stabilized around some number. But if we look at the energy profile, surface energy profile that we are seeing from the LAMP simulation, what we see is that this is a completely different behavior we are observing. It is starting with a higher number, it is going towards a lower number. That's also okay, but if we are able to see that it converges at that number, so that also we are not able to see. Okay, so which means that if I do the solid-solid interface energy calculation using the classical simulation, I really have no confidence in the results I would be obtaining, because neither the surface energies match nor do the behaviors of the surface energies match. Okay, so then what do we do? Okay, because we can't do this by ab initio. Now it looks like we can't do this by classical simulations. Okay, so is there no way out of this? Okay, so then we thought a little bit and we said, how about we follow a hybrid approach? Okay, so what we do is, we do the surface energy conversions through ab initio and we use this information. So we don't do a surface energy conversions by classical simulations at all. We know that this is the number of layers at which our ab initio energies converge. So we simply pick up that number and now we are going to use that as the number or the slab thickness we want to work with from classical simulation. Okay, and so we are going to repeat the calculation for surface energies for these thicknesses, even though the surface energy numbers don't match. Okay, and we'll see what happens. Okay, so now we know how to calculate the surface energies. We know what is the slab thicknesses we need to work with. We need to just make sure whether now at least our ab initio results would agree with our classical simulation results. Okay, so and this is what we see. Okay, so we have a success story here, because we saw that if we took the information for the conversions of surface energies from the ab initio, put it in the classical simulation and simply repeated the same calculation, okay, and looked at the interface energy, because interface energy is just a difference between the total energy and the individual surface energy. Even if those individual surfaces energies do not agree with the ab initio surface energies, the differences do agree. Okay, so which means that this is a very nice agreement that we are seeing between the ab initio and the classical simulation results. Okay, so which means that now that we have been able to validate that we can work with classical simulations, we have a methodology now that will work for the aluminum, zinc and any other, let me say, any other metal alloy interface that we are interested in. Okay, so we follow this titanium procedure for the aluminum zinc alloy that we are interested in. So we do the surface energy conversions for the aluminum FCC 111 oriented surface, and for the zinc HCP 0001 oriented interface. Okay, the first observation we see that the surface energy of zinc is much lower than that of aluminum. Then to get the classical simulation, okay, we need because we are in titanium, it was simple because we simply needed the titanium interaction potential, semi-empirical interaction potentials. For aluminum zinc, now we need in aluminum zinc interaction potentials. And when we looked into the repository that is there at NIST for the empirical potential, there is no potential for aluminum zinc, but there is a potential for magnesium aluminum zinc, where magnesium is a very small, it's a dopant in a very small percentage, they say. And the way the potential is developed, it has the binary potentials as well, binary interactions, which means they have the magnesium aluminum, the aluminum zinc, and the magnesium zinc interactions in the way they have built the potential. So which means that this could work for the alloy that we are interested in. So we use this potential and we obtain the surface energies for the HCP and the FCC surfaces. And in this case, as if you can see here, okay, this FCC is fairly well converged, okay, but this doesn't have as good a convergence profile as the zinc HCP phase. Okay, so we did the surface energy calculations for two surface thicknesses. One is an 18-layer thick surface, and the other is the 24-layer thick surface. And with this, how is the interface energy calculation we have done? So we start with this. So if we are looking at an 18-layer aluminum surface, out of these 18 layers, when we want to get the interface energy, we keep the bottom 9 layers fixed. And for the HCP, we are not fixing anything. Okay, we are allowing all the layers to relax. Similarly, if we have a 24-layer thick slab, we are fixing half the layers. Okay, so this actually I had put in the slide here. Okay, so in the interface calculation, we put a certain keep a certain number of layers fixed and allow the remaining to relax in the interface to determine the energy of the interface. Okay. So with this now, we for the two different slab thicknesses, we get the interface energies, and we see that they are differing very marginally. Okay, so which means that this 18 and 24 layers is a reasonable thickness that we can work with. So we know how to do this now for aluminum zinc. Okay, but what about when we have alloy? Okay, we want to see a surface of a pure metal. Calculation for the surface of a pure metal is simple because I have a very small simulation cell that I can work with. But when it comes to an alloy, I need to have the correct dopant concentration for the alloy, and when I build the surface, that surface should be able to reflect that correct dopant concentration that we have. Okay. So for the aluminum rich alloys, now we have to do the surface generation a little differently. Okay. So what we do is we take the correct orientation of the surface that we are interested in. So we start with the pure aluminum surface structure. Okay. And in this, we find out what would be the suitable number of repetitions for the unit cell that we need to work with, so that we are able to get the correct dopant concentration. Okay, and accordingly now we build the surface. Okay, so this is now the smallest unit cell for the aluminum 95 zinc 5 surface that I can work with, and this is the 60 atom unit cell. And in this 60 atoms, we have doped 3 atoms with zinc. So that gives me the correct dopant concentration. Similarly, for the 9010 now, we have to work with a different unit cell structure. And so this is a smaller than the 95.5, and that always happens. As the dopant concentration increases, we can work with smaller and smaller unit cell. Okay, but the other way, as the dopant concentration reduces, we have to go to very large unit cells to be able to do the calculation. Okay, so we find the surface dimensions that would be suitable, and now with this we will perform the repetitions along the z direction to get the slab thickness. Okay. So this is what we do. We follow the same procedure again. Okay, we are going to fix the bottom two layers for the FCC and relax all remaining in the z direction to get the surface energy. Okay, and similarly for the HCP, same methodology. Okay, so now zinc has a very nice again surface energy conversions behavior, but when we come to the alloy, okay, we require a large number of surface layers as compared to the pure aluminum case to be able to see the good surface energy behavior. Okay, so with this now we have what is the thickness we should work with for the 95 fine and the 9010. We go ahead with it, and now we do the interface energy calculation. Same procedure as we followed for the titanium, and now what we see is that if we increase the zinc dopant concentration, then the interface energy is reducing. Okay, so this and I believe this agrees with what is experimentally observed. I don't have a very good experience working with aluminum zinc alloys. This is the first time I'm working with this, but I think this agrees with what I've seen experimentally as well. Okay, so this brought forward the issue of, okay, for aluminum zinc we were able to find a pair interaction or a semi-empirical potential that works well, and we are able to determine the interface energies of this. But tomorrow if I want to work with a different composition, then what do I do? Unless I have the classical pair potentials, we won't be able to do this calculation. Okay, so parallelly we have also started working with the developing of the semi-empirical potentials for the binary alloy, and because there is a system now with which we can test everything, we started with the aluminum zinc case. We are right now we are only working with aluminum, and the way the semi-empirical potentials are going to be developed is we are going to use the first principles data. And what is the data we are going to look at? The energies of the different structural phases, the elastic constants of these phases, the formation energies if we are working with binary alloys, the defect formation energies, cohesive energies, and all these things we will put into the fitting procedure for the semi-empirical potential. Then whatever potential we generate, we want to validate that produces all the physical properties correctly. Then this is ready for work using in classical simulations, and if it gives us the right results, then we have a methodology that we can reproduce for any binary, ternary, any kind of a potential we want to do. Okay, so for this, I know how to now, I have told you how to obtain the energy for a given particular structure. What about the physical properties that are related with that structure? And the first important property that we have to work with is how to determine the elastic constants from first principles. So typically, many electronic structure codes also have a module that allows one to calculate the elastic constants. And when we initially started working with this module, okay, we realized that the amount of time it was going to require to calculate the elastic constants and give us back the result was going to be in a few months. And so to get just one set of data for one material, we would have to do the calculation not for few days or few weeks, but actually it was few months. and which means that this was not a viable procedure to work with if we want to work with multi-component systems, because every time I change the composition, I would want to know what are the elastic constants for that composition, and that data should be available to me in a reasonable amount of time. It should not take me 8 months to get that few numbers, right? So we followed an alternate method. Okay, so in this alternate method, what is done is that the crystal structure is put under a strain, and we do a Taylor expansion, and by following the Taylor expanded polynomial, okay, we fit for the elastic constants. Okay, so we know this is the energy of the system without any strain. This will be the energy of the system with the strain we have applied. We vary delta, so we know what is the amount of strain we have applied, and so we can compare the energy of the strained and the unstrained crystal, and for doing this for various values of delta, we do a fitting, and we are able to obtain the elastic constants for whichever elastic constant one is interested in. Okay, so we validated this methodology. Okay, why we chose this is because we want this in a reasonable amount of time. We can do this for crystalline as well as polycrystalline materials, and we found that this methodology gave us good agreement with the experiment. Okay, so I'm putting in the data that we have obtained for the work I've been doing with Guru related with the copper aluminum system, and this is the one on which we actually did the first test. So this is basically the elastic constant that we have obtained from the module that is inbuilt in the software. And fitting means we follow the polynomial fitting method that I described just now. Okay, so we see that, and these are the actual experimental ones we expect. So we see that whatever we obtain by the fitting is actually quite well in agreement with what we get not only from the WASP inbuilt module, but they are also in good agreement with what is there in the what is experimentally reported. Okay, so which means that we can follow this methodology for all other systems that we are interested in. I mean, we did this calculation for a set of dopants for set of percentage dopants for aluminum and copper, but I'm just showing you data for one case. Okay, so we follow this methodology and we obtain the elastic constants for aluminum following this methodology. And now there's a reason I have two sets of parameters here. I'll explain to you in a moment. So this is the experimental data. This is the data we obtain when we start with the structure that we have obtained from ab initio calculations. And for that structure, we do this strain method and do the fitting and obtain the elastic constant. And when we use this data in our fitting procedure, which I'm going to show in a moment, what are the results we obtain, okay, we realize that we are getting a slight disagreement in the predicted values. So we thought, okay, maybe it has to do with there being some error in the original lattice parameter prediction from ab initio. So let's not work with the ab initio lattice parameter, but let's start with the experimental lattice parameter. Okay, and we still do the calculation of the elastic constant by doing this strain method, but now the strain is applied to the experimental lattice parameter. And with this, when we do these are the numbers we got. Okay, so it looked like the elastic constants that we were getting from the ab initio predicted lattice parameters were giving us a slightly better agreement than when we started from the experimental lattice parameter. Okay. So, okay, as I said, the reason we did this one, because when we put this into the fitting procedure for the interaction potential, okay, so what you see in the red here is the input that we give to the program that is going to do the fitting of the parameters and generate the semi-empirical potential for us. Okay, and once we generate this semi-empirical potential, we use this semi-empirical potential into a classical molecular simulation software. In this case, we have used it in LAMS, and then we see how this potential is now going to do the prediction for the different structural properties for that material. Okay. So the prediction simply means that after we generated the interaction potential, we now use this interaction potential to obtain the structural properties. Okay, so this is the predicted property, and then we look at what is the how much difference we are getting in the prediction. Okay, so the fit inputs are really our reference. Okay, if my prediction, if my potential generation is very nice, it should give me back exactly what I had put into the fit. Okay, so which means then I have a 100% perfect prediction that is coming up. Okay, it's a very good prediction, but that generally does not happen. So we need to see how much, how well we are doing, and where we are doing well and where we are not doing well. Okay, so which is why we look at this difference. So we see that it gives us a good prediction for the structural parameters. So the structure it is predicting nicely. 4.043, it gives us 4.041, which is very nice. If we look at the cohesive energy, they are also very nicely agreeing. But when it comes to the elastic constant, okay, there is a variation. Okay, and okay, this difference is related with respect to these red numbers that I have shown. Okay, and you see a second row of differences. So that second reference is with respect to what is the experimental observation for those particular values. Okay, so any theory should be able to actually give a prediction that agrees with experiments. Okay, so we should be able to get the experimental results. Okay, so this is what we are looking at. So we see that the elastic constants are really not being predicted that well in our current fitting procedure. So then we said, okay, we started with the ab initio data. Let us try to see if we do the fitting procedure with the experimental data. So we take all the inputs from experiments, we fit the potential using the experimental data, and then we see if this generated pair potential would now give us a better agreement because we have taken it from experiment. So now the expectation is that it should agree with the experimental result. Okay. So what we see is again here, we are doing fairly good job when it comes to the structure and the energetics part. But when it comes to the elastic constants part, okay, it is still not doing really well. Okay, which it simply means that we need to fine tune a little bit our fitting procedure. So that these elastic constants are predicted reasonably well. Okay, which we will do. Okay, and so we again, and the third set of results here is we are comparing how our generated pair potential is doing in comparison with what has already been generated for aluminum and which is available in the repository. So we take the repository potential, and with the repository potential, if we do the predictions for the structure, the energetics and the elastic properties, okay, then we see that the elastic properties are predicted much better than what our prediction is. Okay. So of course we know we need to improve on this. Okay, but between the ab initio and the experimental data, we are seeing that the ab initio predictions are coming out to be a little better than the experimental data that we use if we do for the fitting. Okay. So, as I said, when we develop the empirical potential, generally the potential should work, basically it's meant, should be developed in such a way that it works for a wide variety of properties that one is interested in looking at. So, for that, which means that in the fitting procedure, we need to include more parameters for which we should do the fitting, and a step in this direction is where we are going to include the phase stability and energetics data. So for this we have done the ab initio calculations for the different phases of aluminum. We have and we have compared them with what is there available in the either in the experiment or the literature, and how do the differences between the phases compare with what is already reported. So this is the most important part. So from the energy stability perspective, if I should be able to predict from a particular potential which is going to be the most stable phase for that particular material, and which are going to be energetically less stable phases, and what is the difference between those phases, okay, determines what is going to be the stability. So this we see we are getting good agreement. Okay, so this is a very nice thing. Okay, so to summarize what we have done so far. Okay, so we have found, or let me say, developed a methodology that will help to obtain the solid-solid interface energies for any metal alloy that would be of interest. You can form an interface of any metal with any metal alloy with any metal alloy. Okay, so that is possible. So we have a very general approach now. This is not there in the literature. We have hunted through literature to be able to find a way to determine the solid-solid interface energies, and we realize that there is nothing available in the literature which is generic, which would be applicable for any system that one would be interested in. Okay. So, and we have validated this by doing the ab initio and the classical simulations for the titanium BCC and HCP phases. I'm running ahead of time. Okay. So we see that the classical surface energy predictions differ from ab initio. So for now, it looks like we'll have to use this combined approach where we determine the surface thicknesses from ab initio and use them in classical simulations to be able to get reliable interface energies. But at some point of time, it would be nice if we can bypass this step of having to perform ab initio simulations and be directly able to work with classical simulations. Okay. And we have developed a semi-empirical potential which gives us excellent agreement for structural parameters and cohesive energies. However, it needs improvement when it comes to the prediction of elastic constant. And I thank you all very much for your attention. And if you have any questions, any doubts, feel free to ask them.
I have a few questions. One is, you were talking, I can't see too much of data, but I can still ask you that you have developed a good potential, and the potential second derivative will give you the elastic constant in general.
That's the goal, that the potential we develop should be able to give us the correct structural properties. It also should be able to give us the correct energetics.
So that means elastic constants are a part of the curvature of the potential in some sense. Once I have developed that potential.
No, they go as the.
No, you can do the multi dimensional So you can how do you measure? You do it like how do you measure the elastic constants when you have a potential? You just do the derivative, right? With a particular lattice.
No, we obtain the energy
Uh-huh.
for, so we know what is for a particular structure, okay, we know what is the lattice parameter that gives the minimum energy,
Right.
okay, so this is our base structure.
Right.
So with to this base structure, now we are going to apply strain
So
in different directions based on in which direction, right,
and get the average stress out,
which
right?
elastic constant we want, okay. So we do a fitting procedure. Then based on what is the amount of strain applied, what is the energy you get for that. So you plot the difference in energy versus the strain. Okay, and you fit a parabola. It's a parabolic fitting. You fit a parabola, and from the curvature of the parabola, you get the elastic constant. Yeah.
That it is like you apply strain in certain direction.
Yeah.
You get the stress.
Yes.
You think.
Right.
So if that is so, my question is, if my lattice parameters are coming correct, right? If my potential is good, my lattice parameter, equilibrium thing is coming correct, then automatically shouldn't the elastic constant be coming correct?
No, that's what one would think. Okay, but it is going to determine. See, because the energy is determined by doing the fitting procedure for the electronic densities. Okay, they are determined correctly for the ground state, the minimum energy state. Okay, but there could be some error in the predictions for the other strains. Okay, which the ab initio gives correctly, because ab initio is on the fly procedure. Okay, but for the pair interaction potential, because it's in some kind of a mean potential you are working with. Okay, this to a it depends on how good your fitting procedure is, how good you are able to determine those embedded energies.
No, because I was thinking you are not going very far off in the parabola, right?
No, you don't. You can't even go very far.
Yeah.
It is only within that very small range.
So basically that's what we were also thinking, right? In parabolic approximation that we do. We don't go very far from it. If we go, then we will also be low.
Yeah, so we are looking at only 2% strain in this direction, in this direction.
So that is where my question is. 2%. Is it not large enough?
I mean, if we do it for less than 2%, okay, we have verified this. We do it for less than 2%. We do it 1%, do 2%, 3%. All we have verified. Actually, it doesn't matter so much. Whether I do 1% or 2%, they come out nearly same.
That I have, this is, so elastic constant is where you are basically still stuck in terms of the same. Means other than that, all other parameters like maybe.
No, we have only done fitting using 5 parameters, Shashwata. Okay, one is the structural parameter, the cohesive energy, and the elastic constant. In aluminum case, there are only 3 elastic constants.
Okay.
Okay, so there are only 5 parameters we are using in the fitting procedure. Okay, so my guess is that I need to sit with, of course, Abhishek and see this, that there is something we need to tune in the fitting procedure to get the elastic constants being to be predicted reasonably well than what we are getting right now. It's just a matter of choosing the correct combination of the values, fitting parameters. So although it is quite good, it's still not what I would have expected it to be.
Right. Another small question. That is again coming from a very different layman perspective. You are talking of the excess energy associated with the index, right? And you are calculating every time I see calculate surface energies and you calculate for it. My point is, if I just do 2 slabs with periodic boundary conditions, and these slabs energies I already know, then it is the total energy minus the 2 bulk energies is going to be.
But that is what it is, right?
No, but you are having additionally surface.
No. It is these 2 slabs put together is my interface.
Right.
Okay.
Right.
So I get the energy of this interface, calculate the energy of this interface, and from this I subtract the energy of the individual components.
But the individual components, if I make them fully periodic.
No, they are surfaces.
Why?
It's the same because I'm looking at a surface, no?
No, but so that I understand. But why do I require that? The question is simple. But the question is, if I have it the surface, see, I have the one phase which is bulk aluminum, which is extending infinitely in a.
If you put periodic,
Yes.
you have two interfaces instead of one.
Yes.
How does it change the calculation?
Yes. Does it make it easier?
With the ways are two surface calculation.
Yeah.
No, I'm not following the question. Let me just put back that figure and.
So you say if you replace the vacuum, you don't have that.
No. If I replace the vacuum, then I have in effect a bulk. I don't have a surface.
No, you'll have two interfaces.
You have interface.
Periodic boundary condition.
Yeah.
So you'll have two interfaces.
You have the same interface.
Yes. I would have two interfaces.
And
Yes.
the bulk energy is very easy to calculate. You don't have to even calculate. Means in general.
I think that will be even more difficult because the number of layers will actually go much more.
No. It's periodic. Periodic is smaller.
He has to have that number of layers.
No. See what to form the interface. See the problem. This is what I discussed earlier. Okay. If I want to form an interface which has a minimal lattice mismatch. No. This also answers your question. I think Shashwata to an extent. Because if we look at the smallest case in this case is actually the aluminum zinc, which actually has the largest lattice mismatch. To think of it, okay? Because when we look at the lattice mismatches, this is what we calculated, okay? Pure aluminum with pure zinc, I have a 51% lattice mismatch, okay, in the A and B direction. If I put in zinc in it, based on the dopant concentration, this mismatch reduces, okay. And when we say reduces, it really doesn't reduce very much. We see that from 51%, it has actually come down to 50.8 or 50.7. In 5%, it comes down to 50.8, or you could say 50.9, and in the other case, it comes down to 50.7. Okay, so because there is a very small amount of zinc, the lattice mismatch is also reducing by a small amount. Okay. When I want to do this calculation by, as you said, a periodic kind of a repetition, okay, I need to determine what is the smallest structure I need to generate, which will give me the correct periodicity in the x and y direction, right? So, if I want to get the correct periodicity in the x and y direction for the aluminum surface, for the zinc surface, okay, I need for aluminum a simulation cell which is of dimension 13 by 65. This is, I'm just talking about the XY, okay. And for zinc, I need a 14 by 70, okay. Now, in this I consider only one layer, okay, one layer which is of 13 by 65, okay, for aluminum. Then we counted what is the number of atoms I require, okay, that comes out to be 5070.
Okay.
So which means a periodic calculation is also not possible.
Right. I understand. Yeah.
So the largest, okay, so when we did the surface energy conversion studies here, okay, I didn't tell this, but this case, okay. So for this case, when we did the surface energy conversion study, okay, for 95.5, we went to 30 layers, okay. So 30 layers means already I have a 600 atom calculation there. And when I go to 9010, because as I increase the dopant concentration, I require smaller cells actually. It came down to 300 atoms. Okay, so 600 is still doable with a decent amount of high performance computing infrastructure. We may be able to stretch it till 1200 at the most. Okay, but beyond that, it is going to be very difficult. It's just impossible to get any results within a reasonable amount of time.
Right. That's like I have a limit. I don't know.
No, that's good. Which is why, see, I put in all this considering that this is going to be for an audience which is not an expert in doing first principles calculations.
It's enormous calculation. That's the main problem.
Yes, and no, it's not only enormous, it also requires it takes a large amount of time to just get one energy out. Okay, I mean, if I were to compare it for classical simulation, within few seconds we can get the data. But this, we have to learn for days to get one surface energy number there. So which is why when I said that it would be so nice if we can have, this was there in the summary I put in, no? If we were to able to obtain the surface energy predictions reasonably well using classical simulations, then actually it would bring down the estimation time of interface energies by a considerable amount. All I need is a good potential that would be able to predict the surface energies more or less approximately accurately with what the ab initio gives. What we are saying now is that the interface energy is coming out correct because the differences it's able to predict correctly, but the individual surface energy numbers are not coming out correct. Okay? Shall I? Okay. Thank you very much everybody for your patience.